then, dear colleagues, we can start our section today. And we have 1, 2, 3, 4, 5 presentations for our section today. And first presentation will be offline by Sidorenko Vladislav, Anatoly Neishtadt, and Sheng. And the presentation has titled Stability Analysis of apsidal alignment and
Уважаемые организаторы, можно ли мне после вот этого, уважаемые организаторы, уважаемые, у меня просьба к вам. Организаторы, уважаемые, просьба у меня к вам.
Да, мы вас слышим.
Я хочу попасть на доклад, но на вечер, посвященный Дню памяти Ильи Израильевича Блехмана. Он начинается в 6 часов. Можно ли мне вот до этого времени попасть к вам?
Вы можете слушать, да, конечно, присоединяйтесь к нашей секции.
Нет, еще раз, нам на 18:20 назначен.
Да, 17:20, начало секции.
Ну, а можно ли мне выступить раньше, вот после этого доклада? Потому что, еще раз, на 18 часов назначен вечер, посвященный памяти Ильи Израильевича Блехмана.
У Сергея Павловича доклад в этой секции 18:20, а он хочет пойти в другую.
Правильно, да. Я хочу на 18, ну, на 17.
Поэтому он просит, чтобы ему выступить час раньше.
Да.
А Riabokon Евгений тут у нас? Посмотри, пожалуйста.
Riabokon тут.
Здесь.
Пропустим?
Можно ли мне передвинуться? Я прошу.
Да, без проблем, конечно.
Спасибо большое.
Да, тогда хорошо. После этого доклада.
Тогда у меня следующий доклад, да? Спасибо большое.
Okay. Hello to everybody. I would like to present some scientific results devoted to the dynamics in three-body problems. These results were obtained in collaboration with Professor Neishtadt and his PhD student Sheng from Labra University. But I would like to start with the following comment. Before the coffee break, I was on a section devoted to the memory of Professor Ilya Israelevich Blechman. I met him 1 or 2 times on some conferences, and it's difficult for me to recall did I attend his lectures, but I read his book, and this book produces a strong impression on me. In particular, his book on synchronization in nature and technique. And among the other things, he studied some problems in celestial mechanics. Actually, he published only 1 paper in celestial mechanics, and this paper were published in a proceedings of a conference, not in a serious journal, but nevertheless, one of the chapters in his book is devoted to the resonance motion in a solar system, and his analysis is rather qualified, and his results are reasonable and important. And my colleagues from Keldysh Institute of Applied Mathematics, in particular Professor Beletsky, often mention Professor Blechman as a very creative person. And currently I understand that some of the studies of Professor Beletsky with his students were inspired by Professor Blechman. Well, and even on the cover of this book, you can see the celestial bodies which turn around the star in a resonance. This configuration corresponds to the so-called motion resonance. Okay. But in my talk, I suppose to consider some dynamical problems which connected with the dynamics of exoplanetary system. I mean, in other words, dynamics of planetary system in vicinity of other star. Well, some basic info. The first reliable discovery of exoplanet were in 1992. At that moment, approximately 5,000 exoplanets are known in more than 3,000 planetary system. And 2 years ago, Nobel Prize in Physics were obtained by French scientists Mayer and Claire for the discovery of first exoplanets in the vicinity of Sun-like star, because the first exoplanets were discovered in the vicinity of pulsar. Okay, so can I ask you to switch the animation? Both dynamics of planets in other planetary system may be very different from dynamics of planets in our solar system, because in solar system planets moves approximately in a orbits which are close to the circular with small mutual inclination. In a exoplanetary system, the situation is very substantially different. On the first, one of the exotic examples you will be able to see, you were able to see on this slide. In this case, you see, in certain case, regular dynamics. Both ellipses are more or less oriented in a similar way. The lines of apsid, the lines which connect the apocenter and pericenter of both planets. Here, an example of exoplanetary system with the star and 2 planets. The star in the center, and it's senseless to demonstrate its motion. So the line of apsids of both these planets preserve more or less the same direction. This phenomenon is called the apsidal resonance. Okay, next slide, please. I can do it by myself now. Okay, and it's this phenomena discussed very often in connection with dynamics of exoplanetary system, and for this reason, me and my colleagues decided to investigate the stability of apsidal resonance. Investigation of stability of apsidal resonance in a general situation under the scope of non-restricted 3-body problem. It is in the case when we take into account the masses, in the case when masses of all planets are different from 0, is connected with some technical difficulties. For this reason, we decided to start from the consideration of so-called restricted 3-body problem. In restricted 3-body problem, it's supposed that mass of one body is negligible with respect to the mass of other bodies, of primaries. Usually restricted 3-body problem is considered in connection with the dynamics of small celestial bodies like asteroids. And although our attention to this phenomena, to apsidal resonance, was connected with exoplanetary system dynamics, since we will use model related to the dynamics of small celestial bodies, we will use terminology usual for this field. So I will call the primaries the main body star or sun, maybe the planet which influence the orbital motion of a test particle, I will call Jupiter, and the test particle I will call the asteroid. Also, To simplify the motion equation, we use usual procedure. We will average orbital motion we will average motion equation of the orbital motion. Physically, it corresponds to the distribution of a mass of the planet or of the object around the orbit in a way that part of the mass on corresponding ring proportional to the time which particles spent in this part of the ring. This kind of averaging was proposed by Gauss, and replacement of interaction of particle by, when we study evolution of orbital motion, the replacement of particles by such material rings can be approved mathematically, and actually the modern averaging techniques appears as an attempt to prove the Gauss approximation. Okay, so, and what we will study, we'll study the apsidal alignment when the major semi-axis of orbits of asteroid and of a planet, of a Jupiter aligned. In that case, we can distinguish between the so-called outer equilibrium when asteroid orbits lies away from the planet orbit, and in a case when asteroid orbit is small enough and planet orbit encircles the planet, the orbit of asteroid. Okay, I should say that I did not suppose to write down the motion equation. It's enough for me to mention that we have a stationary solution, and this stationary solution more or less corresponds with our intuition. The only important comment connected with the existence of so-called singular solution which correspond to motion with eccentricity equal unity. So this solution corresponds to motion around the segment. Maybe at the first look, such a solution may be useful-less for real world, but it's not so. It's consideration of this limit case. It's a usual situation when investigation of singularities allows to know more about the properties of processes. But nevertheless, today I will concentrate only on regular solution. Regular solution. So in our case, all stationary solution, all situation of apsidal alignment correspond to regular solution. The complexification takes place only in the inner case. Here I presented parameters which characterize the dynamics in inner case. We have two parameters. One parameter characterizes the value of a semi-major axis of asteroids. I suppose that Jupiter, the semi-major axis of Jupiter equals unity. And the second parameter of the problem is Jupiter eccentricity. So we have two parameters which characterize the general dynamics. So the partition of set of parameters, of value of parameters in the case can be subdivided in four parts. In the part one, we have only regular equilibrium, regular solution. In part two, we have a regular equilibrium and one singular solution, which directed in the opposite side in a in a part 3, we have one regular and two singular equilibrium, but it's also curious enough to find that for some values of parameters, we have no singular equilibrium. Actually, this diagram was constructed in 1982 by my colleague from Keldysh Institute, Professor Vashkovyak, and these regions were absent in his publication. It was some kind of surprise for us when we decided to recompute his diagram, only with the case to draw a picture. We did not suppose that we will be able to find something new. Okay. So here I presented the values of eccentricities, and for different value of asteroid's eccentricity for different value of problem parameter in both in inner and in outer case. And it's most interesting, the stability analysis. Here I presented the problem Hamiltonian, and as you can see from the structure of this Hamiltonian, in linear approximation we have stability of this apsidal resonance. So all quantities here or parameters here are positive, but this Hamiltonian is a quadratic form which is not positively defined. So it means some surprises with nonlinear stability. And to draw a conclusion about the nonlinear stability, we first to apply more powerful techniques, the Arnold-Moser theorem. This theorem provides sufficient stability for condition. It connected with absence of resonance. In this case, the Polar resonance should be absent. Well, the arguments in this Hamiltonian characterize the deviation from exact resonant, exact apsidal alignment. And two variables characterize the deviation inside the plane of primary motion. And two quantities characterize the deviation of apsidal of direction to the pericenter of asteroid's orbit outside the orbital motion. So this frequency is characterizes a small oscillation of direction to upper center of asteroid's orbit around the direction to the upper center of Jupiter orbit. And so for stability, we need the absence of this resonance. There is one more condition which is connected with the structure of nonlinear term in a systems Hamiltonian. So the nonlinear term should be non-degenerate in a certain way. So this quantity should be different from zero. This quantity is called the Arnold Determinant. Okay, so we try to check this quantity. Here I presented the results of frequencies ratio calculation in inner case, results of frequency calculation in outer case. I should say that in inner case, dangerous resonance are absent, but they can be observed in an outer case. Well, we also need to check the non-degenerate condition. We did not compute it in accurate way for all values of system parameters. We computed, we checked the non-degenerate condition in the case of very small values of asteroid semi-major axis. So in a situation when asteroids very close to the sun, or in the case when asteroids are very large. So in the case when asteroids far away from the sun. In that case, we computed Arnold Determinant in an analytical way. We found that it's different from 0, and it means since right parts of our motion equation are analytic function, that this condition of non-degeneracy can be violated only on some algebraic curves, and the number of these, the final set of algebraic curve. So it means that our apsidal resonance is stable almost for all values of parameters. But if it's stable for almost all values of parameters, in other words, the set of parameters where this resonance is stable has 0 measures, nevertheless, for some values of parameters, instability really takes place, and from the analysis of normal form of Hamiltonian in the case of 2-to-1 resonance, we found for what parameters, for what initial conditions, the instability really takes place. Here I presented the results of numerical computation of unstable situation, instability of apsidal resonance due to the resonance to one between the frequencies of oscillation near the resonance in the plane and of the primary motion and out of this plane. And here you can see as motion in which initial inclination of the particle of the asteroid to the plane of primary motion will equal to 1 degree, increases up to approximately 40 degrees. Okay, so the conclusion of my talk. So it was proved that for almost all parameter values of in restricted three-body problems, the apsidal alignment is stable. And for those values of parameters for which the stability has not been proved, there may indeed be the instability. Thank you for your attention. Internet. Okay. We use Runge-Kutta method of high enough order 7, 8. It was enough for our purposes. Because we were sure in our results from theoretical point of view, we apply numerical calculation mainly to check the results of theoretical analysis. Okay.
So, dear colleagues, we have some changes in our program, and the next speaker will be Gorbikov Sergey. Yeah?
Yes.
Yes, and Sergey is from Nizhny Novgorod State University of Architecture and Civil Engineering, and the presentation has a title, Topological Equivalence of Local Qualitative Singularities of a Dynamic System with Impact Interactions. So, please.
Yes, сейчас я войду.
Мы можем расширить вашу презентацию, или вы сами будете показывать?
Ее должен показать, но я что-то не могу понять, где она.
Давайте мы вам поможем.
Вот это видно или нет?
Видно?
Видно?
Можно полный экран сделать. Да.
Ну, сейчас, подождите. Вот полный экран. Видно все, да?
Все видно, спасибо.
Спасибо большое. Коллеги, я могу говорить по-русски? Дело в том, что выше вы говорили по-русски. Дело в том, что если не говорить по-русски, то вам нужно читать, а я буду, грубо говоря, ломать язык. I know English a little. Могу я говорить по-русски?
Да, можете.
Ну, спасибо большое. Так вот еще раз, мой доклад следующий. Топологическая эквивалентность локальных качественных особенностей динамических систем с ударными взаимодействиями. Что это такое? Ну, может, вы не знаете, я скажу. Значит, изучить локальную качественную особенность, это значит изучить малую окрестность этой точки, которая есть качественная особенность. Малую окрестность этой точки в фазовом пространстве динамической системы. И исследовать основные особенности поведения траекторий в этой окрестности. Понятно. А изучить локальные качественные сингулярности и доказать эквивалентность этих качественных особенностей. Это значит, что вы умеете и знаете все свойства, которые вам нужны, и больше никаких свойств вам не требуется. Только эти свойства, которые используются в локальной качественной особенности, я считаю, что только их и нужно изучать. Остальные свойства вам не нужны. И они необходимы просто для вашей эрудиции. Они нигде не требуются. Я вот считаю, что это так. Ну, теперь я перехожу к системе, про которую я буду говорить. Она появилась впервые в работе ну, депонированной, ее сложно найти. Вот эту работу тоже сложно найти. Но, в общем, в 1981 году совместно с Вiercigrochом, с Юрием Исааковичем Неймерком мы написали, он мой учитель, мы написали работу, о которой еще позже скажу. Но вот в ней и уже используется эта система. Это динамическая система. Что это значит? Вот это означает следующее, что ударные взаимодействия происходят на гиперповерхности S равно нулю. Но мы им заменяем на x равняется n равно нулю. Ну, это так проще. Если мы говорим о поведении малом, то, конечно, лучше перейти к конкретному простому виду динамической системы. Второе, значит, ударные взаимодействия обобщают гипотезу Ньютона, ударную гипотезу Ньютона. Вот сейчас это увидите. Ударные взаимодействия происходят мгновенно. И когда xn вот в точке, на многообразии xn равно нулю, xm n равно нулю, x1 равняется нулю. Вот тут все точки, есть точки касания фазовых траекторий динамической системы. То есть все точки касаются именно это все точки касания фазовых траекторий динамической системы вот этой поверхности xn равно нулю. Вот что это означает. Больше ничего в этом как бы страшном виде динамической системы нету, не заложено. Вот еще раз, xn ударная поверхность. И удар здесь происходит, смотрите, любой, но здесь вот еще раз. За счет того, что xn, x1 вот, меняется таким образом, да, это означает, что здесь, грубо говоря, это обобщает, вот это ударное взаимодействие обобщает гипотезу Ньютона. А все остальные, вот видите, переменные в этот момент, когда xn равно нулю, не меняются. Все остальные переменные не меняются. Все остальные переменные вот здесь не меняются, а только меняется. И поэтому вот фазовое взаимодействие, ударное взаимодействие происходит вот таким образом, вот таким образом. Вот от этой точки до этой точки, от этой точки до этой точки. Так, ну и дифференциальное уравнение здесь, грубо говоря, любые, дифференциальные уравнения любые. Ну просто вот это последнее уравнение означает, что вы касаетесь поверхности xn равно нулю в точках x1 равняется нулю. xn равно нулю, x1 равняется нулю. Вот такое поведение фазовых траекторий. Вот такую систему мы использовали, я с тех пор и занимался. Вот эта система. Так. Ну, для такой системы выделены локальные особенности 6 типов. Ну, вот это вот статьи. Ну, в общем-то, они раньше были выделены, но здесь они сформулированы, более-менее внятно написаны. Ну, первые 3 типа, вот первый, второй, третий, они тривиальные. То есть, вот смотрите, первый тип это означает, что вот xn равняется нулю, xn с точкой равняется нулю в этой точке. Вот в точке m1 xn равняется нулю. Ну, она попала, видите, xn равняется нулю. X точкой, xn с точкой отрицательно, то есть траектория касается, падает на эту поверхность, попадает на эту поверхность. Дальше действует ударное взаимодействие. Все, тут ничего особенного нету, и тут говорить о чем-то не имеет смысла. То же самое со второй точкой. Здесь xn с точкой больше нуля. То есть точка – это возрастание фазовой траектории дифференциальных уравнений. Ухода их от поверхности xn равно нулю. Все. Тут еще раз, вот ударное происходит взаимодействие. Дальше точка уходит из малой окрестности. Все, тут ничего особенного нет. Ну, тут то же самое. Третий тип, он фактически тривиально изучается, потому что здесь есть траектории, которые, значит, попадают на эту окрестность, на ударную поверхность, попадают, проходят здесь происходит ударное взаимодействие. Что-то я никак не могу понять. Вот попадают на эту поверхность, происходит ударное взаимодействие, и точки уходят. Или точки просто проходят без всякого взаимодействия, без всякого ударного взаимодействия. Все точки проходят. И здесь есть какая-то особенная поверхность, которая состоит из тех траекторий, которые касаются поверхности xn равно нулю, x1 равняется нулю. xn равно нулю, x1 равняется нулю. Ну, это многообразие называется. Ну и тут важно следующее, что я тут не сказал, я не сказал, что тут, оказывается, в силу ударных, xn с точкой означает, что вы просто рассматриваете уравнение удара при xn равняется нулю. Уравнение движения фазовой траектории при xn равняется нулю. Вот это вот xn равняется нулю, и получается вот это вот условие. xn с точкой меньше нуля, xn с точкой больше нуля, так тоже. Так, что-то я не мог понять. Так, да. Что-то я никак не могу понять, что происходит. Почему не видно? Но я что-то не понимаю. Почему? Что-то я ничего не понимаю. Что происходит?
Мы вашу презентацию видим, может быть, вы пролистали?
Понимаете, что вот тут, может, я просто из нее выйду, а потом войду. Значит, что нужно вот так, наверное, сделать. Сейчас я попробую. Вот. И войти опять войти опять в презентацию, да. Потому что сейчас показывают у меня какие-то части своих. Вот. Теперь все показывают. Вот видите, все показывают точки. Ну ладно, вот, значит, следующее. Ну, третья особенность тоже не имеет, очень простая, и она вот таким образом изучает, причем еще раз, вот эти вот производные находятся в силу дифференциальных уравнений движения. То есть я просто дифференцирую еще раз мое вот это уравнение по времени, причем при условии, что x равно 0, x1 равно 0, больше ничего. Тут ничего особенного нет. Вот. Ну, дальше переходим, значит, к четвертому типу. Это уже самые интересные типы начинаются. 4, 5, 6. Четвертый тип следующий. Первый, значит, xn равняется нулю, xn равняется нулю, x1 равняется нулю, x1 равняется нулю. Получается, что вот на это многообразие попадаем. И здесь условие следующее. xn с двумя точками в силу дифференциальных уравнений движения, xn с двумя точками в силу дифференциальных уравнений движения, я ее вот указал здесь, вот эту xn равняется нулю. Вот это самое, как его, ну вот xn меньше нуля, вот точка четвертого типа должна быть производная меньше нуля. Ну, видите, что это означает, ну, например, точка вот m со звездой и m бесконечно со звездой, это означает, что ее малая окрестность состоит из бесконечно ударных движений. Там только бесконечно ударные движения. А что такое бесконечно ударные движения? Они говорили, во-первых, это написал Макмиллан, он просто привел пример о этом бесконечном ударном движении, но на него не обратил внимания. А вот на бесконечно ударное движение обратил внимание Фейгин, Марк Исаакович, это наш нижегородский ученый, который вот написал работу, первый написал эту работу. А вот Роберт Фаритович Нагаев, ваш уже ученый, он очень подробно использовал эти бесконечно ударные движения. И причем очень хорошо их изучил. Так вот еще раз, в этой вот статье Юрия Исааковича Неймарка и моей, да, вот доказана следующая теорема. Вот я выбираю точку, какую-то, вот точку, да, на правой, грубо говоря, полуповерхности, И вот она участвует в бесконечно ударных движениях. Вот так вот. А что такое бесконечно ударное движение? Это бесконечное число ударных взаимодействий за конечное время. Вы, надеюсь, поняли, да? Я просто это бы написал, но об этом не сказал. Еще раз, вот бесконечно ударное движение. Видите, оно вот доходит до сюда, касается, пересекает, затем происходит ударное взаимодействие, затем опять траектория выходит, значит, происходит ударное взаимодействие и так далее, и так до бесконечности. Так до бесконечности. Вот эти бесконечно ударные движения изучал Фейгин и ваш Роберт Фаритович Нагаев. Вот. Ну, мы доказали теорему следующую, что вот эти все точки, М1, вот точка М1, М2, МЖ, МЖ плюс 1 и так далее, вот до бесконечной, до самой конечной точки, они лежат на траектории гладкого дифференциального уравнения. Причем мы пишем его уравнение. Мы не пишем это уравнение. И причем вот этого факта оказалось достаточно, и вот он только и нужен для того, чтобы доказать локальную особенность, локальную эквивалентность вот этих вот особенностей. То есть ничего больше не нужно, кроме вот этой вот теоремы. Ну вот, смотрите, я привел пример, ну вот, пример касается системы вибротранспортирования. Этой системой занимался Илья Иванович Блехман. Еще в 1964 году он написал монографию «Виброперемещение». И вот сегодня ему будет посвящен вечер на вашей конференции. Вот сейчас он уже начинается, я так понимаю. но я хочу на него успеть. Поэтому прошу прощения, я занял чье-то время. Так вот, эта система виброударное взаимодействие, причем, значит, вибротранспортированное, причем транспортированное без вот вибротранспортирование и транспортированное без, ну, да, вот просто вот транспортированное с подбрасыванием, просто с подбрасыванием. То есть вот я написал при W меньше единицы, и эти все точки, вот эти все точки, являются бесконечно ударными, причем четвертого типа. Вот эти все точки являются четвертого типа. И здесь вот траектории, я нарисовал две траектории этого дифференциального уравнения, которые, вот еще раз, я выбираю здесь вот точку, да, точку М, она скачет сюда точку, потом скачет сюда, потом скачет сюда, и так далее, скачет сюда, 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 и так до бесконечности, до вот этой точки. И вот эти все движения по этим траекториям я обозначил вот этими стрелками. Движение по этим траекториям, точка еще раз начинается здесь, она, грубо говоря, перескакивает сюда, потом сюда, потом сюда, потом сюда, потом сюда и так далее до бесконечности. И кончается точкой t равняется 2π. Вот таким образом здесь можно провести пример. Дальше шестой тип локальной особенности. Что означает, что в этой точке xn равняется нулю, xn с точкой равняется нулю, xn с двумя точками, которые я написал, равняется нулю, x с тремя точками уже можно написать x с тремя точками, но это не просто сделать, да. Ну, это просто сделать, но это очень много времени, места занимает. Очень много места занимает при записи вот этого условия. Просто продифференцировать вот это. Но не это надо, а дифференцировать вот это уравнение при условии, что x1, xn равняется 0, больше ничего. Особенного ничего здесь нет. Получается третья производная, и она должна быть отрицательной. Вот еще раз, все траектории малой окрестности вот этой точки. Вот у меня точка М, это точка 6 типа. И вот все фазовые траектории рано или поздно попадают в область бесконечно ударных движений, в которых работает уже наша теорема. Вот это вот, я, который сказал, моя теорема. Ну, это наша с Ш.М теорема. Вот, но она на самом деле пишется по-другому. Ну, в общем, это самое главное, что она вот здесь работает. Это означает, что вот, чтобы доказать факт топологической эквивалентности вот этих вот точек, больше ничего не нужно. Поэтому еще раз, вот эти точки попадают рано или поздно в малую окрестность, в которой действует дифференциальное уравнение. Вот уравнение движения по этой траектории. Это дифференциальное уравнение. Траектория дифференциального уравнения. Вот траектория дифференциального уравнения. Вот она. И вот больше ничего для доказательства этого локальной эквивалентности в этом случае не нужно. И, наконец, пятый тип, он самый сложный, да. Но я тут доказал, но еще не опубликовал этот результат. Он состоит в следующем. Вот смотрите. Вот у меня точка, локальная особенность пятого типа. Что это означает? Что все производные до второй включительно равны нулю, а третья производная положительно. И вот в этой производной, еще в этой точке производная тоже. Это означает, что траектория выходит из нее. Вот все траектории, вот смотрите, вот находящиеся от гамма-1 до... Что такое? Вот от гамма-1 до вот этого многообразия, да, вот эти вот все точки, они уходят без ударов. Вот все уходят без ударов. А дальше вот смотрите, вот между кривыми гамма-n и гамма N1, N плюс 1, да, существуют n ударные, начинаются на между этими кривыми, в точках между этими кривыми, начинаются траектории ударных взаимодействий, во время которых происходит n ударов. Это означает, что вот между этой точкой гамма-2 и гамма-1, вот здесь все точки у меня расположены вот здесь, участвуют в одном ударном взаимодействии, после которого траектория уходит из малой окрестности, этой локальной особенности. Малой окрестности локальной особенности. Вот. А теперь что? Есть вот траектория кривая гамма со звездой, в которой накапливаются вот эти вот гамма-n, которые не накапливаются. Она предельная для этих траекторий. И здесь существуют бесконечно ударные движения, которые подчиняются дифференциальным уравнениям. Вот это здесь у меня в этой работе они написаны. А дальше вот здесь, вот от гамма со звездой до этого многообразия x1 равно 0, n равняется 0, вот до этого многообразия. Вот во всех этих точках существуют бесконечно ударные движения. И эти бесконечно ударные движения касаются, в них
Одна минута осталась.
локальные особенности. Ой, сейчас, я уже кончаю. У них действует траектория дифференциальных уравнений, о которых я говорил. Все. Больше ничего для доказательства локальной эквивалентности этих точек пятого типа не нужно. Ну и дальше я привел пример. Это означает, что вот это вот есть многообразие, множество области область бесконечно ударных движений. И вот здесь используется, применяются мои дифференциальные уравнения. Вот здесь, вот в этих вот точках применяются мои дифференциальные уравнения. И следующий, я привел несколько незавершенных проблем, которые требуют своего внимания, я считаю. Вот все, если хотите, я уже на этом закончу.
Сергей, спасибо большое за доклад. Коллеги, у кого-то есть какие-то вопросы?
Мой English is bad.
Онлайн, Кирилл.
Thank you for your attention.
Да, в таком случае спасибо большое, Сергей. Отправляем вас на встречу.
Спасибо большое. Дай Бог вам здоровья. Спасибо большое. А как же мне ее отключить-то надо, да? Что я не понимаю.
Нажмите Escape на клавиатуре.
Ну да, и теперь как же выйти-то? Спасибо большое. Дай Бог вам здоровья. Всего хорошего. До свидания.
Всего доброго. Спасибо. So the next speaker is Riabokon Evgeny from Perm National Research Polytechnic University with their presentation Experimental Studies of the Mechanical Characteristic of Rocks under Dynamics Loading.
Good afternoon, ladies and gentlemen. Is my presentation is seen well?
Yes.
Okay, great. Thank you for introducing myself. So yes, I will talk about our results on experimental studies of such rocks as sandstone. And this project is conducted in the framework of Russian Science Foundation. And let's me start. So this is a brief structure of my presentation. So I briefly introduce the problem, then we'll speak about the experimental methodology, how we prepared samples, how we determined linear elasticity zone, and then how we perform dynamic tests. By the end of experiments, we found nonlinear nature of dynamic Young's models. Based on that, we formulate the model. Found first, let me say, intermediate result of our project, and I will also tell what will be the next steps in our project. So, introduction. Elastic properties of sedimentary rocks change under dynamic loads or vibrations. The knowledge of how geomechanical characteristics varying is very important in several fields, in particular geotechnical engineering, such as well construction, production or injection wells, mining, and etc. Studies on the nature of rock Young's models variation under the dynamic loading are not common, mostly due to complexity of custom-made experimental setups and how to interpret the obtained results on those installations. Nevertheless, in references, you may find several papers, experimental papers, that describe in which during experiments on saturated rocks, dispersion of dynamic Young's modulus can be found, and it is observed dispersion of Young's modulus is observed between 10 till 1,000 or somewhere 100 hertz. At the same time, there is only a few papers on experiments on dynamic loading on dry rocks. So here you may see that the variation of dynamic Young's modulus is not observed. However, the plots which are presented here correspond to very small strain rates, up to 10 powered minus 6. However, in mining, in well drilling, for example, as I already said, the rock experienced much larger strain caused by vibrations of drill string and drilling bit, and therefore behavior of the Young's modulus can be different at high strain rates. So, in order to see the behavior of mechanical characteristics at higher strain rates, up to 10 powered minus 2, we conducted experiments. And here are small explanation of how we prepared samples. So basically, we studied 4 types of samples depending on their diameters and lengths. So we used special coring and cutting machine to prepare the biggest one with a diameter of 24.7 millimeters, and we used diamond drilling bits to prepare the smaller samples. And here is a block of sandstone, which was actually sourced from the Scotland's, in particular in Clashas quarry. It was extracted from. So we manufactured these samples through coring, cutting, washing, drying procedures, which is basically standard for studying the rock samples according to this ASTM. After we prepared those samples, we determined linear elasticity zone for all of them. So this is an example of a tenuous Hounsfield field with smaller sample in between the plates. And actually for all of these 4 samples, we determined basically, obviously, standard load contraction curve, which starts with compaction, then it continues to linear elasticity, where Young models can be calculated from this trivial formula, and it ends with the irreversible strain, where cracks starting to propagate and finally breaks the sample. After we determined, we did it for 9 samples from for each diameter of the sample, and we averaged them and determined the maximum stress average and minimum average stress. So those values, which are shown here, were correspond to linear elasticity zones. So further, next step was to study these samples in this elastic zone during dynamic loading. So in order to do that, we created a small experimental setup where this specimen or sample was placed in the middle here on this plate and was subjected to static load and dynamic loading produced by piezoelectric actuator powered with signal generator, where we were able to change frequency and amplitude of the dynamic load. The strain of a specimen was measured by horizontal strain was measured by vibrometer, and axial strain was measured by eddy current probe. The force was measured by Kessler force sensor. As a result of our experiments, we obtained basically this diagram. Exactly 3 readings gathered from eddy current probe, vibrometer, and force sensor or external load. So we studied each sample at 30 patterns, which means we tuned frequency for 15 Hertz, for example, and amplitude for 50 Hertz. And so this pair of 2 parameters were changed. So 30 regimes were in total in order to see the difference of dynamic Young's modulus depending on the combination of these parameters. Dynamic Young's modulus was calculated from this equation, which is very known, and as a result we obtained this kind of nonlinear surface, which is characterized in terms of in 2D, which is characterized by a rational function in terms of amplitude of the dynamic load, and by quadratic function in terms of frequency. So in order to produce a model of what is happening here, we started to digging the information over the references, and basically this kind of inertia, this kind of dispersion of elastic Young's modulus can be caused by inertia. This is mentioned in very famous paper of Zhang and Zhao, and the reasons for such inertia can be viscous and plastic, not can be, they actually are viscous and plastic mechanisms or structural effects. Those microcracks, viscous behavior of rock matrix between cracks, and structural inertia forces. However, these effects are observed when rock is not compacted, and in this first reference, the example is shown proving that. In our case, the rock was compacted. It was preloaded with static load. So the microcracks of our samples were closed, and microstructures were in tight contact. So it was like a solid body. By doing this, healed rock represents a solid medium in which viscous and plastic effects are blocked, and associated with them dispersion of elastic modulus is not observed. In such conditions, in a sample, there were only effects related to acceleration of a load applied, with dynamic load applied, axial inertial resistance of a rock to load. So we interpreted it like this: axial inertial resistance of a rock to the load. So the model of the dynamic Young's modulus should consider only the inertial effects related to external non-stationary load, using pretty classic approach of Jagger we used mass on spring, where A is a sample at the rig, actually in our experiments, and B schematics of the model. So here, and the next slide, there will be some derivation of the model. Briefly, displacement of mass on spring from an equilibrium position sets delta L, from which we can determine its short, like the short length of our specimen, and L max is the maximum length of our specimen in the cycle of loading. So we use standard laws, and considering that this is elastic force, loading samples carried out according to the law. And by doing this, we say that description of a rock sample upper and down motion is mathematically reduced to studying the dynamics of mass on a spring. One assumption we did the displacement of all the points, no matter where it's located, goes according to the same law regardless of location, as already said. According to Goldstein, we used equation of displacement, and by doing some mathematical tricks, we finally obtained the model 10, which describes behavior of dynamic Young's models. In these models, alpha is a ratio of frequencies of natural and external oscillations. As you may know, there are several oscillations, including internal of a body, and C is a reaction of a rock sample to external load. Since omega exceeds the frequency of this disturbing oscillation, then alpha will be much higher than 1. And by analysis of experiment data, we found that alpha was 5,000. Parameter C was chosen based on frequencies, amplitude, mass, length, and diameter. So the first milestone of the research will be the following. So basically, we conducted experiments and found the behavior of nonlinear behavior of mechanical characteristics, in particular dynamic Young's modulus. So this dynamic Young's modulus is expressed in this model. But the thing is, we solved only one-dimensional task because the loading was only uniaxial. But in fact, in geotechnical engineering, for example, in well drilling, here an example, a rock is experiencing three-dimensional strain, and in order to model this condition and to see how dynamic characteristics will be changing, we have to use special. We have to build custom setup. But so when we search for the data, we found in papers that there are several installations already exist in the world, but this strain rate is small, as I already mentioned several slides before. In order to overcome this issue, we actually can use we could use split Hopkinson bar, but and it will give us a good strain rate up to 10 power 3. But the problem of split Hopkinson bar is that we cannot model cyclic deformations. So we have to move forward and search for another installation. So in these slides, you can see the standard for this kind of experiments installations. They are custom built, and in this installation, for example, here you may see this is the sample, and the sample is loaded with axial loading from the top. It's subjected to non-stational loading from oscillator, and here around the sample is a liquid which models like horizontal pressure, which is actually located in the subsurface. And so this kind of experiments model real conditions, and we would like to go in this way because these installations all of these installations mostly dedicated to geophysicist research. It corresponds to frequency only up to 10 powered 2, and very small strain up to 10⁻⁶. And this the kind of installation which we are now going to manufacture, to build. This is pretty standard installation for our tasks. So this is the sample. This exactly loaded with axial loading, and around it is a liquid which creates pressure. But even this installation, which was like a year ago created, only could give 10⁻⁵ strain rate. So we require that at the moment the new custom rig using we will use standard installation Electro Plus Instron Electro Plus E10000, which corresponds to maximum load 10 kilonewton, and we will use 3-axial cell here, and we will like create a special measuring system which will be able to give us information or on Poisson ratio and dynamic Young's modulus. So we will be now going to closing remarks. I would like to say that over 250 dry sensor samples of a cylindrical shape and 4 different sizes were tested. Our small custom-built rig allowed for inducing controllable dynamic uniaxial compressive load via piezoelectric transducer. The obtained results have confirmed the strongly nonlinear nature of the new red sandstone Young's modulus, but which I needed to say that the only one-dimensional problem is solved. So we need to move now to the 3-dimensional nonlinear loading, and we will tune up our existing installation for our needs for that. So that's the reference which were seen in my presentation. Thank you for your attention. I will be happy to answer your questions. Thank you.
So Evgeny, thank you for your presentation. Dear colleagues, your questions. So Evgeny, I have one quick question about your experimental methodology. Did you develop the methodology yourself, or did you use like a ASTM standards or something else?
Yes, as you already seen. So during preparation, we used very standard methodology during preparation of samples, and during experiments we developed based on existing methodologies which we read over the references. We developed our own, which is pretty close to what's happening in other universities, in other research groups. So like that.
Okay, thank you for your answer. Any question? So thank you for your presentation, Evgeny.
Thank you.
And the next speaker is Rybalova E from Saratov State University with the presentation Dynamics of Autowaves under the Influence of Noise in a System of Coupled Map-Based Neuron Models.
Yes, thank you. And first, I would like to start with some concept which will be meted in my own work. So the first study of spatial temporal structure is in active nonlinear media. have take great part in science of investigation of structure. And the main beautiful example of this structure it is after-wave structures. And of course, I would like to demonstrate the Belousov-Zhabotinsky oscillating reaction. First video, on the first video, we can see target wave structure, which fill all space of media. And the next video demonstrate spiral wave structure in the same reaction, but in this example, we should have some external influence, for example, heating, or add some reacted in all. And of course, if we speak about after-wave structures, we should know about dynamics of heart. In the normal stage, heart demonstrate target wave with length more the size of heart. And if when we have some disease, tachycardia, fibrillation on the heart, we can see spiral waves. All video can demonstrate this. For this video, I use site the virtualheart.org, and they have a lot of model of nonlinear media with different type of afterwave structure and just neuron dynamics. And of course, in my work, I should not chimera state. Before 2002, investigated in synchronization in network of identical oscillators was not very interesting. But Kuramoto and Batok had produced two breeds in this sphere, and they open new structure in ensemble of non-locally Kuramoto phase oscillators, identical oscillators. They had shown that in this ensemble we can see coexistence of coherent cluster and incoherent cluster. This structure was named chimera state. It's special temperature structure in network of identical non-locally coupled oscillator. On the next slide, we can see very beautiful experiment with coupled pendula of Kapitanik and other. This cluster of pendula have synchronized dynamics, and the other on. Sorry, I think it's not very good video. You can find it in this paper with better, but like This they show that pendulum can demonstrate coexistence of coherent and incoherent cluster. So, and of course, I think nobody or not a lot of people investigate, have investigation chimera. So if not, they was found in biology. And it is, of course, dynamic on heart muscle. In this work also shows that dynamic of heart muscles very close to the dynamic of spiral wave chimeras. It's spiral wave structure with incoherent core. And the other example of chimeras in biology, it's unispheric sleep, which we can find in brain of dolphin and some swift. When their one sphere of brain have low and dynamics and other high dynamics. And until 2019, all works can also scientists could find only spiral wave chimera like this. But after my colleagues can found after wave chimeras with a target wave. It's concentric or target wave with incoherent cluster. In this work, they have coherent cluster, but with the different dynamics. And after this, we found a structure like this spiral wave chimeras and target wave chimera in a two-dimensional lattice of map-based neural models. We took Rybalova neurons as map-based neurons. You can see equation of these neurons and plan of parameters with different dynamics area. It's absolutely classical dynamics for neural spikes, silence, and burst of spikes. In our work, we investigated lattice of these maps with local couplet. It means each element couplet only the nearest neighbor, like this. For example, ij elements connect with only this square, this and this. Number of elements which couplet with our elements depends on their address on lattice. So we fix parameters sigma, it's coupling strength between elements, and also after when in latest spiral wave or target wave established, we add noise with normal distribution and the like intensity. So On the plane alpha sigma, it's parameters, control parameters of Rulkov neural map. We found area with spiral waves. It's shown on this, and two different regions with target waves. They have a different core. So I start from target wave because of noise influence. It's not isn't interesting in this case. So time of evolution of target waves. First, on lattice, we can observe coherent dynamics. After this, some area, some region appear with different dynamics, and this region in some time period start to produce waves. So it means it's a pacemaker for target wave in this structure. For target wave of the second type, firstly, we can observe coherent plane with some solitary nodes. It's not very good, but solitary nodes on J equal 150 and I 100. Like this. So these solitary nodes in future can produce also target wave. If we have influence, noise influence on target wave of the second type, nothing observe, and I would like to show example only with target wave first case, first type. So when we have small influence of noise, it's small intensity and small size of these structures, nothing happen. But when we have very high intensity of noise, target wave change their structures, waves, and now we can see that noise influence, external noise influence, produce a new target wave. And when we turn off our noise, these structures isn't disappear, and we can observe we can observe target wave chimeras. For the spiral wave, if we say about time evolution of spiral wave, first on the plane lattice we can observe solitary nodes, it's yellow dot, and after some after wave structure appear, but in very long period they disappear, and we can see only one spiral wave. Sometimes it's destroyed, and on lattice arise more than one spiral wave, but in long time period, which depends on initial condition, all spiral wave structures died, and we can observe only coherent structures. In this case, external noise can destroy spiral wave, but we can see spiral wave in this case. However, when we have very big size of noise influence or very high intensity, spiral wave destroyed it, and on lattice arise target wave with incoherent cluster. After noise is turned off, all structures correspond to coherent dynamics. So in this case, we made diagram in the influence region size, noise intensity parameter plan, which shows the possibility of transition from spiral wave to target wave. In gray region, transition is observed. In black isn't. And in orange, this transition from spiral to target wave depends on initial condition and noise realization. So some conclusion and our work on this topic. Thank you. Noise? Sorry, couplet or noise? No, noise. Okay. Localize it in center of lattice with, for example, it's pink square with size 3. And after this, I name it like S noise equal 10. It means square 10 by 10. No. Eight. We choose it. Why we choose this number of elements? Okay, number of elements we choose like. Let's try it, and choose better. It better between time of modeling and structure which can absorb on this lattice. And coupling exchange, we have a lot of experiments with all parameters. Coupling exchange, coupling radius are parameters of map, and choose this because of in this case we can find spiral and target wave on this plan, on this parameter plan.
So the next speaker is Ismailov Shamil from Moscow, from Dukhov All-Russian Scientific Research Institute of Automatics, with a presentation, holographic and interference method for registering their surface shape in gas dynamic experiments.
Good day. My name is Shamil Ismailov. I'm going to present a report on holographic and interference method for registering the surface shape in gas dynamic experiments. A surface topography is changed when the plates and enclosures loaded by shock wave in gas dynamic experiments. The studies of the inertia, displacement, features, and deformation of the shock wave loaded surface and can be informative in terms of properties of the loaded material and the mode of its structure. Method based on holographic interferometry allow use to extract data on the changes in the surface shape under different effects on materials such as heat shock. In gas dynamics, it is currently crucial to study how the surface topography changes under shock wave loading. In order to investigate dynamics of structure materials, the gas dynamic experiments are now to widely use various laser interferometric techniques. When a motion of a continuum is registered, the techniques enable to accurately measure a speed and position of the tested region on the surface. However, it is not so easy of the structure of the sample is destroyed, resulting in fine particles, so-called dusting. An existing digital holography is one of the methods to specifically record the dynamics of particles in a dispersed phase during fast processes. Holography is in some way a flexible approach to detection of fast processes. It helps record not only a cloud of fine particles, but probe the sample surface to high precision, which is also of great interest for us. And due to irregular shock waves, the surface suffers deformation, which causes differences in height that scatter light, which reduce the effect of conventional holographic techniques. Thus, it is necessary to search for methods which enable to register the shape of dynamically changing surface under shock wave loading. The paper objective is to investigate potential for detecting change in the surface topography of shock wave loaded samples using holographic and interferometric techniques. The following tasks have to be solved to achieve the objective. Study possible detection of the surface topography by means of a Sheng interferometer. Estimate the utmost capability of the method for reconstructed change in the surface shape applying the Sheng interferometer. To perform a holographic diagnostic of the surface micropattern from various materials, experimentally process the structured light technique. Sheng interferometers are widely used for checking quality of optical surface, recording the structure of gas flows as well as in holographic interferometry. Sheng interferometry exploit an arrangement of the microinterferometer, but with mirrors to couple two identical light beams displaced relative to one another. The interference between the two identical beams obtained in the interferometer is enabled to make it possible to reconstruct a wavefront structure of a source beam. The slide shows a schematic of the shearing interferometry operation. A light divider and mirrors divide the light from the point source S into flow switch from an interference pattern on the photodiode array detector. The interference pattern is equivalent to the which will be generated so the interference of two coherent sources. If the investigate object is not a point source but a float reflecting surface, then each point of the interference pattern will maintain a constant difference of phases. The interference pattern itself will be a system of parallel fringes. If there is a local inhomogeneity at the surface point, for example, cavity or rotation beams stemming from this point, will have a constant path difference with respect to adjunct points. The interference pattern depicts it is a show of the fringes proportional to the path difference and consequently to the inhomogeneous magnitude as shown in the right slide. Thus, the studies of the shearing interference pattern taken from the inhomogeneous surface can help define the magnitude of the change in the topography at each surface point in the direction of the wavefront displacement. The experiments explored two possible wavefront displacement from a remote object. In both cases, a concave dish of the reflecting telescope is used to eliminate a region on the object and to transport emission scattered from the object. There is the shearing interferometry in the receiving path, but which generated the interference pattern on the photodiode array detector. The Michelson interferometer is used based on two mirrors and a beam splitting cube. In the first case, a lens is located in the vicinity of the investigate object for the elimination emission to penetrate thought in on the product surface and the scattered light to be projected onto a collision aperture of the telescope. In the second case, there is no additional optics near the object, but an intermediate image formed by the telescope dish is transmitted and magnified by means of a projections lens. The provided slide shows shearing interference pattern of the region on the test object coin, which is acquired with the use of the first arrangement. The image clearly illustrated a shear of fringes on the interference pattern in the regions where the topography changes and the age of one on the coin. Thus, the arrangement with the lens on the object demonstrated that it is possible to record the shearing interference pattern, but its quality allows us to estimate changes in the phase qualitatively rather than quantitatively. That of the interference pattern of is processed by a typical reconstruction algorithm applied in digital holography for focus image holograms. In the show on the slide, the initial interference pattern is subjected to a to the Fourier transform to accumulate a complex Fourier spectrum. Then a later maximum of the spectrum is distinguished and is offset by a value of the carrier reference frequency of the interference pattern matching the Fourier transform from a reference plane inclined wave followed by convolution with the signal wave. For employment, the second arrangement of the detection system mockup or a high magnification is provided, and consequently a higher quality of interference fringes is observed. The slide shows a general view of the detected interference pattern and depicts a magnified section with visible interference fringes. The enlarged area is put in a red box. The MAX software is used to simulate an interference model which reflects the experimental arrangement. The CAD draw part of shown on the slide is taken as a test object. There are 4 groups of geometric of various design on the object surface to ascertain the utmost capabilities of the method. The first group intended for detection slopes on the surface. The second, for objects of different height. The third, for objects of different cross sections. The fourth, for object with a non-planar surface. The test object is mounted in the interferometer model in the place of the reflecting surface with geometry towards the prodding laser beam at the wave. As the rays pass the interferometer, the detector generates the image exemplified in the left slide. 2 methods are used to reconstruct the image. The standard processing method described in the previous section and the one based on the Czerny polynomials. The interference pattern obtained allows us to identify a profile of the wavefront of the emission reflected from the surface and calculate a phase differential displaying the changes in the profile shape of the reflecting surface. The phase component of the interference pattern is calculated using the first method in image. For the second method, we use DFT fringe, which is intended to assess the surface quality of mirrors and is applied of designing astronomical telescopes. The program enables to estimate the surface quality by the Foucault method and with the use of the Czerny polynomials based in interference patterns. The 3D pattern of the phase distribution is shown in figure A. It is prepared in image and displaying the changes of the surface topography with method in your case demonstrates more distinct borders of objects as compared with the Czerny polynomials. The data on the nature of changes in the tested surface occurred by the Foucault knife edge show method figure C is qualitatively and makes it impossible to calculate a height of objects in groups of objects on the test surface. It is unfeasible to measure parameters of individual groups by means of the reconstructed image of change in the surface shape, applying the data collected by the Czerny polynomials shown in Figure B. Since the polynomials used for calculation do not provide a local assessment of the reflecting surface and due to a significant difference in the height of groups. Therefore, the local assessment of interference pattern is performed based and on geometric groups. We carry out experiment using a conventional holographic arrangement when a reference beam and an interfaced one between which interference occurs and added up this method in the list fit for your experiment. Science roughness on the surface leads to speckles and destroy the interference pattern. In addition, real samples of structure material invariable occur significant roughness RZ10 at shock wave loading. However, we managed to destroy the surface of the 5 and the 10 Arapov coins in the laboratory, which allowed us to qualitatively evaluate the surface irregularities. This slide presents an optical arrangement for detecting the surface topography by the use of structured light. The arrangement consists of a continuous wave laser, a telescope, and an interferometer. It generates two coherent beams of the required aperture, which are joined on the surface of the sample, forming interference fringes, and the topography structure is displayed in the displacement of fringes. The emission reflected from the shock wave loaded surface is collected by the telescope lens and arrives to detector through a beam splitting cube. The slide describes the processing steps for the recorded interference pattern to extract data on the surface topography. The source interference pattern undergoes to the fast-forward transform. Later component is distinguished from the spectrum, figure 3C, and placed to the middle of the spectrum instead of the zero component. Then an inverse fast-forward transform is carried out, which gives 2D distribution, which an actual and imaginary component. Next, the obtained distribution can be used for a pixel-by-pixel calculation of the phase of the wavefront scattered on the object. In order to have the continuous phase distribution, the phase has to be linked and places of phase discontinued. The experiments are performed on the sample which offset relative to a stationary surface distance of 250, 500, 750, and 1000 micrometer. The slide shows interference patterns where can observe a fringe shift with each displacement which is confirmed by a plot which by a plot with a share of fringes as a function of the sample displacement. The bottom slide demonstrated the reconstructed surface topography of the sample. Conclusion. Thank you for attention. Да, конкретно, если исследуем конкретно вот эти вот случаи, которые я описывал, конкретно для постановки этого эксперимента нам больше подходит последний метод, который основан на анализе структурированного света. Метод голографической регистрации, он больше подходит в лабораторных исследованиях, когда уже в взрывных экспериментах он не подходит, и из-за того, что там уже динамика, все намного сложнее. Спасибо.
So, and the last speaker for today, but not at least, is Tostik Tatiana from St. Petersburg, from Institute of Problems of Mechanical Engineering, Russian Academy of Science. This her presentation, Attraction Basin for the Generalized Kapitsa Problem of Stability of Inverted Pendulum. You can start.
We consider the generalization of
Tatiana,
Kapitsa pendulum problem.
Tatiana, we don't see your presentation, unfortunately.
Attraction basin for the generalized Kapitsa's problem of stability of inverted pendulum. Next slide. We consider the generalizations of Kapitsa's pendulum problem. The simplest problem of this class is the problem of the stability of the vertical position of an inverted mathematical pendulum with a vibration of supporting point in the field of gravity force. The problem was first published by Stephenson in 1908. More detailed theoretical and experimental studies were carried out by Petr Leonidovich Kapitsa. Various generalization of this problem and approximate methods was published by Ilya Israelovich Blechman in 2018. The classical problem of Kapitsa is to study the stability of an inverted pendulum under the action of harmonic vibration of the support. The stability under the action of polyharmonic and random vibration of the support was investigated. Attraction basins of stable position are constructed. The first 6 figures shows the vibration of the pendulum in one vertical plane under the action of vertical vibrations of the support. The last figure shows the problem of spherical movement of pendulum. Next slide. We consider stability of movement of an inverted pendulum with a vertical vibration support. The pendulum is a thin, homogeneous, non-deformable rod of length L. A nonlinear linear differential equation with variable coefficients describes the movements of the pendulum. This is equation 1. Consider polyharmonic vibration of the support. Then the sum of harmonic vibration within the mean square amplitude and mean square velocity. And then dividing the velocity by the amplitude, we get the typical frequency omega 0. The small parameter epsilon is set as a ratio of the support vibration amplitude A0 to the length of the rod L. The nonlinear differential equation 1 with two small parameters, epsilon and q, proportional respectively to the amplitude and reciprocal of the square of the frequency of the support vibrations. The boundaries of the stability of the zero solution of the linearized equation 1 are known and are presented as a fragment of the Einstein diagram. Next slide. Let us find an expression for the region of attraction of a stable solution. For this, we introduce a small resistance into the nonlinearized equation of motion. And we will seek a solution to the Cauchy problem with non-zero initial conditions. We will seek a solution in a form of a sum of periodic functions with slowly varying amplitudes. Applying asymptotic expansion at the third step in the second approximation, we obtain a differential equation for a slowly varying amplitude U0 and find the condition for the stability of the solution is in zero approximation. This condition is marked in red. And next slide. The analytical solution was verified numerically. The graphics of the exact solution and averaged solution were built. These graphics show the attraction for exact and averaged solution to the stable zero solution corresponding to the upper position of the pendulum. Next slide. The boundary depends on the initial phase of initial phase beta, which is unknown in the general case. That is why we introduce two attraction basins in the plane of parameters, GA absolute and GP partial, such as the stability condition is fulfilled for all values B in basin GA, and it is fulfilled only for same values B in basin G-P, and it is never fulfilled in path G0 of plane Phi0Q. Graphic in right of the slide. Condition of stability is convenient to qualitative analysis in the phase plane. The trajectories shown for Q equal to 0.3. Trajectories shown for dimensionless damping coefficients n equal to 0. A bold curve separates the attraction basin. Next slide. The next generalization of Kapitsa pendulum problem is the Kapitsa problem with random vibrations of the supporting point of the pendulum. Let the vertical vibration of the supporting point of the pendulum is F be specified as a stationary random process Xi, which zero mathematical expectation and spectral density S. The nonlinear equation of pendulum vibration will include the second derivatives of the random process we have specified. The process Xi, which will be modeled, must have a second derivatives, which we must take into account when choosing the spectral density S of this process. Just like before, then we had a problem with the sum of harmonic vibration. We find a mean square amplitude and mean square velocity and typical frequency omega 0. The small parameter epsilon is set as a ratio of found vibration amplitude of the support to length L of the rod. Then, similarly, we introduce the slow time and obtain the differential equation for the initial approximation U0 of the slow component of the angle phi in the two-scale expansion. We find a condition under which there will be stability and a stability zone. Next slide. Consider an example in which we approximately simulate a Gaussian stationary random process in the form of finite sum of a series. Sufficiently accurate calculation we obtained for n equal to 200 of the interval lambda from 0 to 2. The boundaries are shown in the graphics. Region GA is region of absolute stability, independent of the implementation of the random process. The GP region is a relative stability, each point of which is in different implementations leads to both the upper stable position and the lower stable position. Region G0, the region of instability of the inverted position of the Kapitsa pendulum. The dark bold lines indicate the stability limits obtained using the initial approximation of the averaged solution. Thin lines are the boundary obtained for the random process Xn, according to the formulas for boundaries given to the previous page. The red dotted lines are the boundaries of stability region obtained by integrating the nonlinear equation of motion of the pendulum. The results show that the boundaries of stability region for harmonic vibration differ significantly from the boundaries obtained by random vibrations. Next slide. The problem of the stability of a Kapitsa pendulum with an elastic support is solved similarly by the method of two-scale expansions. Two regions of attention are obtained, which are realized depending on the initial conditions. Next slide. As before, a non-deformable homogeneous rod of length L and mass M is considered. Its upper end is free and lower one is attached to the vibration support. Introduce the spherical coordinates psi and theta. The second equation of system is integrated one time. So we can express psi with dot and get one equation. Next slide. We proceed the equation with dimensionalist coefficients. In the top of slide, equation in the top of slide. The parameter alpha is taken as a small parameter and solution is sought in the form of an asymptotic series. In their approximation, stability conditions for U0 are found. Blue formula. Next slide. In the absence of friction n equal to 0, the angular momentum of the pendulum relative to the vertical axis is a constant value. The first integral of the system can be written out. The phase plane constructed numerically is shown in the graphic. There are 2 points of attraction, U01 and U02, and one unstable point in fast trajectories, U0 plus, through which the separatrice passes. The dotted lines limit the region of initial condition under which a return of vertical is possible to any initial phases beta. These lines are sinusoids from the initial condition. The phase trajectories satisfy equation with different values of the full energy. Maximum full energy in the left point, U0, U01, minimum full energy in the right point, U02. Next slide. Here are shown the areas of attraction constructed numerically according to exact equation for different values of rotation velocity. Вот они. Next slide. We have considered various generalizations of Kapitsa pendulum problem. We have obtained analytically the condition of stability and the attraction bosons of a stable solution. In all cases, the attraction bosons consists of two parts, absolute and partial. I will be happy to answer your questions. Thank you for attention.
Tatiana, thank you very much for your presentation. Any questions? Tatiana, yes, I have one quick question. Did I understand correctly that you solve your problem not only analytically, but also numerically?
Да, yes.
Okay, and which software did you use, or did you create some new code?
Use. When use?
Я могу по-русски спросить, Татьяна?
Да.
Мне просто стало интересно, вы использовали какое-то программное обеспечение, чтобы найти решение, или писали код самостоятельно?
Да, просто в математике, ну вот еще один студент, он тоже считал это, но я не знаю, в чем он считал. И еще можно показать график, вернее, показать движущуюся картинку действующей модели этого, которую нам Блехман подарил.
Да, конечно, будет очень...
Тогда я свой экран демонстрацию, да, сделаю?
Да, давайте.
Угу. Мам, иди посмотри. Это он проходит через резонансы. Все.
Да, спасибо большое еще раз, Татьяна, за ваш доклад. Да, можно.
Вот вы показали результаты эксперимента, у вас есть численно-аналитическое моделирование. Вы вот сравнивали результаты экспериментов вот, с результатами вашего численной формулы и с численным моделированием и аналитической формулой?
Таких результатов у меня нету экспериментальных, потому что это же веревочка. Но я вот когда в Москве была, в Уфе, вернее, когда я была в Уфе на съезде по теоретической механике, то там были тоже доклады на тему действующего маятника Капицы трехзвенного. И у них он действовал, они тоже его считали. Но мне не дали как бы посмотреть на него. Вот так вот. Численные и аналитические я сравнивала, да.
Хорошо, еще раз спасибо большое, Татьяна, за ответы на вопросы. И на сегодня мы заканчиваем. Спасибо всем за внимание. Хорошего вечера.